Hello, everyone. Today, let's finish the chapter 3.4, multiple expansion. Now, let's talk about the origin, the effect of the origin to the multiple expansions. First, let's take an example of the effect of origin to dipole. So we mentioned earlier that a point charge at the origin constitutes a pure monopole. If it's not at the origin, then it's no longer a pure monopole. For example, if we see the figure in 3.32, we will see now if we have a charge Q, let me draw some lines here. If we see the charge Q, which is not at origin, if we move the origin to the left side of the charge Q, then this charge, even the single charge, can form a dipole moment, which is P equal to Q D, and the direction is in the y direction, of course. Then a corresponding dipole term is in its potential. The monopole potential is not quite correct for this configuration. And exact potential in this position becomes this equation. And the multiple expansion is a series in inverse power of R. And when we expand 1 over R, then we get all powers, not just the first power. So that means by simply moving the origin, then for a single charge Q, the dipole term appears. If the Q is in the origin, is at the origin, then it's a purely monopole, but if you shift it, then you get dipole. So moving the origin can alter the multiple expansion. And the monopole moment Q does not change since the total charge is obviously independent of the coordinate system. Ordinarily, the dipole moment does change when you shift the origin, but there's an important exception. So if the total charge is 0, then the dipole moment is independent of the choice of origin. So here, it means here, for the single charge Q, when we shift the origin, we see the expansion changes. It's simply because the total charge is non-zero because it's a single charge Q. So let's see a case of total charge to be 0. Now let's see figure 3.33. If we displace the origin by amount A for some charge distribution, which is shown here, and we shifted either the coordinates or the charge distribution by a vector of A, then let's calculate the dipole. And if we suppose after you change the coordinates by a distance of A, then the new dipole is P bar. And what you can do is you can calculate the dipole moment P bar, which is shown here using this equation. The integral of R prime bar, which is shown here, rho R prime, which is the charge density of the charge distribution in the new coordinate system, and d tau prime. It equals to r prime subtracted by a, because this is r prime bar, it equals to the r bar subtracted by a times the charge density and then d tau prime. And then you can write this term into two terms, which is r prime rho rho r prime d tau prime subtracted by a rho r prime d tau prime. And this term becomes p. It's the dipole moment in the origin or original coordinates, and then subtracted by this term. This term, you can calculate it, it's q a. A is the difference between the new and the old coordinates. And then now this is a relationship between the dipole moment in the new coordinates and the dipole moment in the old coordinates. The difference between them is a QA. Now, the difference between them is QA. So if so A is a vector. So if Q is 0, then there's no difference. That means if the total charge of the any charge distribution is 0, then the dipole moment is independent of your origin. So no matter which coordinate you choose, it doesn't matter, because the difference between a new and old dipole moment in different coordinates is QA. So if Q is 0, then the difference is 0. In particular, if Q is 0, then P bar equals P. So if someone asks for dipole moment in the figure A shown here, you can answer with confidence it's QD, no matter what coordinates or what origin you choose. So it's always QD. But if you're asked for a dipole moment in the figure B shown here, we can see the net charge of this charge distribution is non-zero. Then the appropriate response would be with respect to what origin, because it's origin dependent. Okay, so far we have been talking about the electric field, and now so far we have talked about the electric potentials, and now let's consider the electric field. Let's calculate the electric field of a perfect dipole if we choose coordinates so that P is at the origin and points in the z direction, which is shown here. Then the potential at r theta is given in the previous equation. And then the dipole, if we consider the dipole term, then the dipole term could be written in this format. It equals to P dot product r direction, the direction of r, which is shown here, and then over 4 pi epsilon 0 r squared. It equals to the magnitude of P cosine theta, and theta is the angle shown here, over 4 pi epsilon 0 r squared. And then in order to get the field, we can take the negative gradient from the potential, and then it will have 3 directions: in r direction, theta direction, and phi direction. In r direction, partial v over partial r, it's 2p cosine theta over 4 pi epsilon 0 r cubic. And then in theta direction, the gradient is, if you use the knowledge of spherical coordinates, then you will get it's P sine theta over 4 pi epsilon 0 r cubic. And then for phi direction, you will get 0 because it's independent from phi, as shown in this equation. Then finally, if you sum the three terms together, you will get the electric field of a pure dipole in spherical coordinates. It's shown here, P over 4 pi epsilon r cubic times 2 cosine theta in r direction plus sine theta in theta direction. So that's the equation to calculate the electric field for a dipole in spherical coordinates. And this formula makes explicit reference on the particular coordinate system, which is spherical coordinate system, and assumes a particular orientation for P, which is in Z direction. It can be recast in a coordinates free form, analogous to the potential in equation 399. And you can solve this problem in 3.36. Notice that the dipole field falls off as inverse cube of R. If you look at this term, it's 4 pi epsilon R cubic. So it falls off in 1 over R cubic. The monopole field goes as the inverse of square, of course. And the quadrupole field goes like 1 over R to 4, and octupole is decreasing in 1 over R to 5, and so on. So this merely reflects the fact that monopole potential falls like 1 over R, dipole falls like 1 over R squared, and so on. And then the gradient introduces another factor of 1 over R. And figure A shows a pure dipole, and figure B shows the electric field line for a physical dipole. We can see for pure dipole and physical dipole, the only difference is if you kind of squeeze the distance between this is positive charge and this is negative charge. If you squeeze the distance between the positive and negative charges, then you can get a perfect pure dipole electric field line, which is shown here. Or if your R is much bigger than D, which is the distance between positive and negative charges, then you will have the field of physical dipole becomes a pure dipole field. Okay, so this is just intuitive figure to show you what does the electric field look like for dipole. And that's all for today's class. Thank you, everyone.